Hey, what's up guys? So I want to start this video off by asking you a question. If you wrote some sort of software application for your computer, how would you turn on an LED in the outside world? Or how would you read in a digital input? So basically what my question is how would you go about talking to the outside world from a computer application? And I think most of us would answer this question by introducing an intermediate microcontroller into the mix, so that your microcontroller talks to the world and it communicates this information up to your computer through some sort of communication interface like USB or serial or Bluetooth or maybe even Wi-Fi. But I don't think a lot of us would consider communicating to the outside world directly. So in this video, I kind of want to show you a discovery I recently made with a very popular chip, actually, by FTDI. It's the FT232RL. And you can put this chip into a mode where you can actually toggle the outputs of this pin. So you can actually, from your application on your computer, turn on and off outputs or even read in inputs from the outside world. So let me show you what I'm talking about. All right, so check this out. This is my Ultimate programmer board here set up with a push button on the, let me see here. It's connected to the TX line and an LED connected to the RX line. So we're not using this chip, the FT232, as a USB to serial converter, but rather more like a USB to general purpose I/O converter. So I have an application running on my computer right now that is basically just monitoring this input, and if it ever sees it go high, it turns this LED on. So if I do that, you can see that it actually does work. So it's really cool. I'm not sure if it's perfect for every application, but it's really cool because chances are you have this chip laying around somewhere or some breakout board for it if you don't have my board. So this chip will give you 8 pins. I only give you three pins on this board. I give you TX, RX, and DTR. There's 5 more that are not broken out on this board. And then there's also 4 extra pins on top of that, the C bus pins. And right now on this board, I have just C bus 0 and C bus 1 broken out. And those are connected to the LEDs. So let me show you that real quick. So here it is, just flashing C bus 0 and C bus 1. Just using those as outputs. You could use them as inputs as well. You can't really use them both at the same time, or at least what I've found so far. So you can either use just the 4 C bus lines or the 8 data lines. And that's how I'm going to refer to things here. So let's jump over to the computer and talk about how you get this all set up, because there are a few things you need to do. Okay, so once you plug the board in and the drivers install, everything's good to go. And I'm talking about when you plug in your breakout board for the FT232RL. You're going to want to download this utility from FTDI. It's FT Prog, and it's free, and I'll have a link in the description on where you can get this. But you download this, and we need to change a few things, so this utility will let you do that. And you want to go and hit this magnifying glass here, and it'll read in the board here, FT232R, and you want to click this hardware specific tab and then make sure that load D2XX driver checkbox is checked. So now it will change from loading the virtual COM driver to loading the D2XX driver, which allows you to communicate to those pins directly. It puts it into a specific bit banging mode. So let's expand hardware specific, go down to I/O controls, and these are those 4 C bus pins I was telling you about, that if you want these to be controllable, you have to change these from, you might see like TX LED, RX LED in here, change these to I/O mode, and then you can go in and read those as either digital inputs or digital outputs. C0 and C1 are my TX and RX LEDs on my Ultimate Programmer board. So if you don't want to use those, just leave this part alone and you're good to go. So next you want to program this, so hit that little button there and then go ahead and hit program. It'll program it, finish programming. Then what you need to do, and this is important, you need to unplug the device and plug it back in. And when you do that, you'll notice that a new driver, a new software little window will pop up, and install the new D2XX driver for the board. Okay, so now I'm going to show you the application side of things and the code I wrote for the application to blink the LEDs and read the inputs in. And for this, I'm going to use Pelles C here, which is free. So you might be using Java or Python or Visual Studio or something like that. But I'm going to just, for the purposes of this video, I'm just going to show you it in Pelles C, which is also a free download. And I'm just going to do this from a brand new project here. So I'm just going to click console application wizard here. And let's just go test here for now. Okay. Yeah, that's okay. Main C is fine. Open that up. And I'll just get rid of all this crap. And I have a text file over here I'm going to copy in the code I know works. Okay. So this is the code. You can see there's a whole bunch of includes here. And the most important one here is this FTD2XX.H. So what you need to do is when you download the drivers, you need to grab that header file and put it in the include folder for the Pelles. So let's go ahead and do that real quick. Okay, so when you download the drivers, the D2XX drivers from FTDI, they come in a zip file which you unzip. Open up that folder, go into CDM V2, whatever this folder is here, open that up. And since I'm doing this on a Windows machine, you have to go in, select your operating system. So I'm i386 there. And you need to drag over some files into the Pelles C directory here. So go to Program Files, Pelles C, and then you'll see the three folders here, the bin, the include, and the lib. So here's what I did, and I'm not sure if this is exactly right or if this is all needed or not, but I did it and it works, so there you go. So open up the bin folder, and you want to grab the .dll file here from this one. Oops, oh crap. I just clicked something bad. But anyway, you want to go and grab this ftd2x.dll, grab that, copy it over, yes. You have my permission. Then you want to go to the include folder, and this is where you'll go back a few notches here to the ftd2xx.h, and you want to drag that one over, copy. Yeah. And then you want to go to the lib folder, and you want to grab this .lib file here, the ftd2xx.lib. Grab and copy that guy over. Okay. And now you should be good to go. Okay, so now if you went to go and build this program, you're still probably going to get an error, and that's because you have to set up one more thing in here. So go into Project, Project Options, go to the Assembler tab, no, not the Assembler, the Compiler tab, and make sure you have this checkbox here selected, Enable Microsoft Extensions. Okay, and then you should be able to go and build this thing, and it should say done. So it was a success. Usually you get a little bit more than that. Okay, there we go. So I'm getting a warning here that I have an infinite loop in there, so that's okay and I don't care. So basically what we got here though is a whole bunch of includes, a whole bunch of stuff. I don't even know if it's all needed, but this is test code, so it kind of doesn't matter. So let's just walk through this very quickly here. So here's how you set up the D2XX driver. So this is how you define it first with the FT_ handle here. We're going to call it all FT handle. You need some other things here to communicate to the device. So this is in some of the actual instructions to read and write from the device. And we'll talk more about that in a second. Here I have some commented code out here to tell you which pins are which on my Ultimate Programmer board. So you can see pin 22 is the RX LED, 23 is the TX LED. You have DTR on pin 2, RX on pin 5, TX on pin 1, and then you also have the bits here that correspond to which bits of the 8-bit bus. So when you're writing to it, you know which is which, or reading from it. Okay, so we have a whole bunch of subroutines here, but I'm going to skip down a little bit here. Actually, I'll just close all these guys a little bit. So we don't need to talk about all of them. They're all pretty much copies from another. So what we have here, though, it jumps down into the main loop here. And the first thing we do is initialize the USB. So if you go up to this subroutine, so I'm going to go from here, and it jumps up to here, and basically it opens up the device. So a lot of this is just copied directly from the user manual, the programming manual for the D2XX protocol. I'll have a link in the description for that. Anyway, that's how you initialize it. I'm sure there's a lot more things you can do there. So you open it up and then you set the baud rate of it. Okay, and then from there you jump into an infinite loop, and each one of these things is like a call to it. So you can just comment things out. So, you know, if you want to blink LED 1, you uncomment that out. And that will blink the LED on the C bus. And the C bus and data work differently, and I'll explain that here in a second. So if we start off with C bus here and jump up to the blink, that subroutine, you see blink C bus 0. So what we do is we use this instruction here, FT set bit mode of the device we're talking to. And what you're doing here, there's 2 hexadecimal numbers. You'll have to look at the manual, but the first one actually tells the device which pins are inputs or outputs and what you want to do with those pins. Do you want to write them high? Do you want to write them low? So when you're in C bus mode, which is this byte here, this defines the mode, which is hexadecimal 20. And in this case, the upper byte or the upper nibble defines whether or not the pins are inputs or outputs, and it's a bit representation of the pins. So if they're all 1s, they're all going to be outputs. Okay, and that's what an F is there. The lower part of the nibble defines what you want the pins to be at. So in this case, I'm writing them all low. So they're all 1, 1, 1, 1. So all 4 C bus pins low. Okay, and then I have to call to another subroutine here, print IO state. And if you jump to wherever that is here, basically what this does is it gets the status of the pins. So FT get bit mode of the device and the address here of bit mode. Don't worry too much about this. And then basically what I do is I clear the screen and I print off what the status of the pins are. So if I went and run this, I think I should be able to do that. Okay, so you could see here what I'm doing in the print IO state subroutine here. So I'm just blinking, in this case, yeah, I'm only blinking the 1 pin. So you could see I'm printing the hexadecimal representation of the pins. So the upper part of the nibble, like I said before, defines what you want the pins to be, inputs or outputs, and the lower part of that byte is what the pins actually are. Okay, so sorry I'm kind of rushing this video, but anyway, that is the print IO state. So I do a little sleep here of 100 milliseconds, and then I write that same pin. Since I'm only blinking C bus 0, then I just need to then make the lowest part of that lower nibble 0, which would be E, right? So that would be 1, 1, 1, 0. So now it'll write that pin low. And then print IO state and sleep for 100 milliseconds. So I hope that makes sense. So I'm just blinking 1 pin, the first pin. Okay. And because, and the reason it's like this and not like, 0, 1, 0, 1, it's because to turn the LED on, I need to write a 0 to it. So actually, when I'm writing a 1 to it, it's actually off. But since I'm grounding the LEDs through the part, in order to turn the LED on, I need to write a 0 to it. So that's exactly what I'm doing here. Okay. So moving along here, C bus 1 is actually the same thing, but I'm just now toggling the next bit. And actually, let me see if I can run that here for you and show you what that looks like. Okay, so now you can see that I'm just toggling the next pin over. And I don't think I need to show you that subroutine. But next up here is to blink the actual data pins. So you have these 8 GPIOs. And if I go to blink data 0 here, TX, and run that, I think I'm safe on my board here to do that. Okay. Let me bring this over here. Okay, so now you can see I'm blinking the TX, but you'll notice that the hexadecimal representation up here is a lot different. And that's because it is, because you can't, unlike the C bus pins, I'm going to expand to C bus here, subroutine. So C bus was broken out. It was using the same byte to tell you which pins are inputs, outputs, and which pins you want to write high or low. But when you're writing to 8 pins total, you can't do this. You need an entire byte to send out just to tell which pins are high and low and which pins you want to actually write high or low. Anyway, so let me go to that real quick here. Data 0 and show you how this is all handled. So the data pins are actually set up so that you're writing data to them. It's like a parallel port. So you can just stream a whole bunch of data, or you could just write a single byte to the pins, and that's what I'm doing, and then you can use them just like general purpose inputs and outputs, right? So what you do here is same thing as before with the C bus. You do a set bit mode of the device, and then you have two bytes, but notice that the mode has changed. So now we're in asynchronous bit bang mode, and that's what this 0-1 is. And this byte here sets all the pins up for their whether you want them to be inputs or outputs. So in this case, all 8 pins are set to outputs. They're all 1s. Okay, then to actually write to the pins, if you want the pins to be high or low, you have to do this command, and I'm going to skip over this for a second here. You'll see FT_write, so of the device, and then you have the actual data you want to send over, and then you tell it how much data, and then you have this thing that says how much data was actually written. And that's kind of the way I think it all works. But basically, to write what you want to the device, you set up this TX buffer to just be just one single byte. So you might have noticed up here that I have this byte, TX buffer, and it's set to just be a single byte. So I'm only going to send 1 byte to the device. So when you do an FT_write of it, and you just have to set the first TX buffer to be whatever you want it to be. So in this case, it's a hexadecimal 0-1. So it'll make the first pin there high, which is my TX pin here. I think that's what that is. Yeah, bit 0 will be high in this case. So it'll write to it, make it high, wait a full second, and then I change the TX buffer to a 0, and then you write that. So it's just toggling that pin high and low. Okay, so pretty straightforward there. Now I'm just going to show you how I mix inputs and outputs on the same device. So if I go here, TX, actually what I'd rather do is show you inputs here. All data inputs here. So just TX, RX, and DTR. And if I go to that subroutine here, you'll just see that the bit mode here is then that first byte, everything is a 0, meaning that all inputs, all data pins are inputs. And the mode, again, is 0-1, so it's asynchronous bit bang mode. And then I go and print IO state. And the IO state handles the monitoring of the pins. So that's how you figure out what is actually happening on the pins. So actually, if I go to that, I could run this one real quick here. Okay, and if you ever get this access is denied error, that's just because you have an instance of the program running. So let's go ahead and do that again. So right now, all pins are inputs, and if I push that first push button there on the TX pin, you'll notice it goes high. But when you look at the status of the pins, you notice they all are being read in as 1s. So it's like they all have pull-ups enabled. So to get a digital input, I'm simply grounding the TX pin. I'm pulling it low. And then I'm doing a little bit of conversion here, or inversion here, just to show you, reading in a 1 or displaying a 1 when a button is pressed is a little bit easier to read than the other way around. So that's basically what I'm doing there. And let me go back here. And that works for all 8 data pins. In the next part of code here, I have a read in the TX in and map that over to the RX out. So this is a mix of input and output here. So let me jump over to that guy. So in this case, what I'm doing is setting the bit mode for 02. So what that means is everything in the byte, the entire 8-bit data bus, is an input except bit 1, right? So if you're starting at bit 0, that would be a 1. Bit 1 would be a 2, and then bit 3 would be a 4, 8, 16, etc., right? So I'm setting bit 1 up to be the output in this case. So that's where my LED is. On the RX pin, the bit mode is still a 1, so asynchronous bit bang, and then I go to print IO, and then basically I have a little if statement here. So if 1 is ever ANDed with the not of the bit mode reading, then I want to write to my TX buffer a 02, which so that'll actually make the LED go high, and then I get an FT write and I shoot that out the pipe to the chip to make that LED go high. Otherwise, make the LED go low. And I know I'm kind of going fast through this, but that is the void TX in RX out subroutine. So that reads in inputs and writes them to outputs. So that's a mix of input and output for this part. So anyway, you know, this video isn't really made to show you anything particularly useful, because I think a lot of us would introduce a microcontroller into the mix for this sort of thing. But, you know, if you're writing an application and you don't want to have hardware side code, I mean microcontroller side code, you know, this is the easiest way of doing it. So, and you can see I'm just communicating directly to pins on that FT232. So it's kind of cool. And anyway, that is the video. Thanks for watching.